Hi, good day to everyone. My name is Suziana Evin and my metric number is 23019. Today our group will present our project presentation where we constructed and demonstrated a soda can steam engine model to illustrate the first law and second law of thermodynamics. Alright, this slide shows the topic objective. The objective of this project was to build a functional soda can steam engine model to vividly demonstrate essential thermodynamic concepts such as the phase transition, heat transfer, energy conversion, and increasing entropy through an interactive experiment. Next, this slide explains about the first law of thermodynamics. The first law of thermodynamics states that energy cannot be created or destroyed. It can only be transformed from one form to another form. Here, we see the heat from the candle increasing the internal energy of the water, causing it to transform into steam. The high pressure steam is then expelled, converting the thermal energy into rotational kinetic energy, as demonstrated by the soda can model. Let's move on to the second law of thermodynamics. The second law of thermodynamics states that entropy or molecular disorder in an isolated system always increases over time. We observe this principle in action as the water transitions from a liquid to a gaseous state, increasing the disorder of the molecules. This can be visualized through the analogy of a deck of cards. Initially, the cards are in ordered, low entropy state, but once shuffled, they reach a high entropy, randomly disordered arrangement, just like the increased molecular randomness when water turns to steam. And that is all for me. Thank you.
Now I'm going to explain more about this history significance. Understanding the law of thermodynamics was crucial for the development of steam engine technology during the Industrial Revolution. Pioneering designed by Thomas Newcomen, James Watt, and George Stephenson harnessed the power of steam or thermal energy to produce mechanical work by the first law of energy of conservation. However, this power generation also necessarily increased entropy following the second law of entropy increase principle. Next, we would like to present our demonstration video. Here's a footage from our soda can steam engine demonstration. We can observe the water turning to steam as heat is added, increasing the internal energy according to the first law. The high pressure steam is then expelled through angled holes, generating rotational kinetic energy. However, as entropy increases, the rotation eventually stops when no more steam is available to power it, illustrating the second law. Next, I'm going to explain more onto the experiment process and the methodology part. To construct our model, we gathered a soda can, a candle as a heat source, a needle and a string, and a support structure where we have used cardboard as our support structure. We made a hole near the bottom of the can and we pour out all of the soda out the can. After that, we have filled the soda can with small amount of water using the small hole made before. Then we made another hole with the same angle for the steam to escape directionally. Then we set it up the experiment and suspended it over the candle flame and waited a while for the can to rotate.
Now we proceed with our result from our experiment. As the candle hit the can, we observe the initial vaporization of water after approximately 10 minutes. This delay was due to heat transfer inefficiencies and environmental heat loss, which are common in a real-world system. Here are some key factors that contribute to the initial delay of around 10 minutes before the soda can start rotating in our experiment. First is thermal conductivity of material. The aluminum soda can has relatively low thermal conductivity compared to metals like copper or iron. This slow downs the rate of heat transfer from the candle flame to the water inside the can. Using a material with higher thermal conductivity could reduce this delay. Second, insulation properties. The soda can act as a basic insulator, preventing rapid heat transfer to the water. Lack of insulation around the can allows heat losses to the surrounding air. Adding an insulating material like styrofoam around the can could minimize these losses. Heat loss to surroundings. Some of the heat from the candle is inevitably lost to the surrounding air via convection. Heat can also be lost by radiation from the hot can to cooler objects nearby. This unwanted environmental heat loss reduces the heating rate of the water, minimizing exposure to air currents, and using a contained heating setup could have. So, for surface area and water volume, the small surface area of water exposed to the heat source limits heat transfer rate. Using a larger volume of water will increase thermal inertia and delay heating. The optimal water level balance heat absorption and vapor generation rates. By addressing this factor through improved design and installation, we could potentially reduce the initial delay before steam generation and rotation begins in the soda can model. Once the water reaches its boiling point, the steam escapes through the angled holes, causing the can to rotate. The rotation speed peak at around 35 revolutions per minute between 12 and 18 minutes, indicating the maximum conversion of thermal energy to rotational kinetic energy. However, as the water supply was exhausted, less steam was produced and the rotation slowed down, eventually stopping completely by 20 minutes. This decline in rotational speed demonstrates the depletion of the energy source and inevitable increase in entropy as detected by the second law of thermodynamics. Now we continue with discussion. As for thermodynamic principle, first law of thermodynamics, heat from the candle transform into a mechanical energy in the form of rotation. Second law of thermodynamics, increase entropy observed as water vaporize and expand, increasing the disorder. As for the efficiency and heat loss, they have initial delay, approximately 10 minutes for the can to start spinning due to heat transfer inefficiencies and environmental heat loss. Heat transfer mechanism, conduction through the can, convection from the flame, and radiation from the heat source. Potential improvements, better insulation, optimized hole placement and size, and minimizing external heat loss. Key observations for initial vaporization, heat from the candle causes water to boil, turning into steam. For the peak rotation, steam escapes through angled holes, spinning the can and reaching a peak of 35 revolutions per minute between 12 to 18 minutes. Decline in revolution per minute as water is used up, less steam is produced, and rotation slow down, stopping completely by 20 minutes. Here are some key thermodynamic principles observed in the soda can steam engine experiment, along with the potential source of inefficiencies and losses. Energy transformation. The chemical energy from burning the candle is converted to thermal energy in the form of heat. The energy increases the internal energy of water, causing a phase change to steam. The high pressure steam is expelled, converting thermal energy to kinetic energy. This demonstrates the first law of thermodynamics, energy transformation without creation or destruction. Second, entropy increase. The phase of change from liquid water to gaseous steam increase molecular disorder or randomness. This rise in entropy is evident from the increased volume and dispersed molecular motion of steam. As entropy increase, the rotation eventually stop when no more ordered steam remain. This exemplifies the second law. Entropy of an isolated system can only increase over time. Heat transfer mechanism. Conduction through the aluminum can transfer heat from the flame to the water. Convection plays a role as heated air or combustion gases transfer heat to the can. Radiation from the flame and heat ca- can surface also contribute to heat transfer. Potential inefficiencies and losses. Heat losses to the surrounding via convection radiation reduce heating efficiencies, efficiency. Low thermal conductivity of aluminum and lack of insulation inhibit heat transfer rate. Friction between the string of support and resistance from air impedance and impedes rotation. Non-ideal steam flow through angle hole lead to inefficient thrust generation. To improve efficiency, design factors like materials, insulation, steam nozzle geometry, and minimizing frictional or heat loss would be optimized. Precise quantitative measurement will enable calculation of actual efficiencies and entropy change. Now we have reached our conclusion. In conclusion, the soda can steam engine model successfully demonstrate the fundamental principle of thermodynamics, including energy transformation and entropy increase, through a simple and practical experiment. To further enhance this experiment and deepen our understanding, we recommend incorporating quantitative measurements, exploring alternative heat source, investigating practical application, and optimizing the design. Thank you for your attention and engagement during our thermodynamics project presentation. Thank you.